This video focuses on Riemann sums and volume, which are concepts that set the stage for our double integration work, and more generally, our work with multiple integrals. To start, let's go back to single variable calculus. For a function of one variable, the area bounded by a curve and the x-axis on the interval a to b can be approximated using a Riemann sum of rectangles. And we had a few options there. We could do a left-hand approximation, a right-hand approximation, or a midpoint approximation. Now, extending into 3 space, for a function of 2 variables, the volume bounded by a surface and the xy plane over the rectangular region a to b on the x and c to d on the y can be approximated using a Riemann sum of rectangular prisms. So geometrically, our integrals are now going to define volume bounded by a surface and the xy plane. For both these definitions, we are assuming that the function is positive, so above the x-axis or above the xy plane, and we'll talk about what happens if the function was not positive. Notation, we're going to see this notation with the x in the middle for rectangular regions, and the order there is x by y, important to note. So, looking more into those rectangular regions, here we have a rectangular region that has been divided into smaller subrectangles. So we have from A to B on the x-axis, and from C to D on the y. So those intervals on the x and y define our rectangular region, and then we're breaking it down into subrectangles. The more subrectangles we break this region into, the more accurate our approximation is going to be. And the way we break these down, so we would say this is x0, x1, and we go all the way to x sub m. So we are breaking down the interval from a to b into m subintervals. So that subscript does play a role. That tells us how many subintervals we broke down into. And then along the y-axis, very similar. So we'd have y0, y1, all the way to y sub n. And that's setting up n subintervals. Could be the case where m and n are the same. In this case, just to throw some numbers out there, 1, 2, 3, 4, 5, 6, 7. M is 7, and n would be 6. Right? So we broke the interval from a to b into 7 subintervals, and then from c to d, we broke it into 6 subintervals. Now let's focus on one of these subrectangles to talk about the rectangular prism that is above that subrectangle. Okay, so let's expand it out. So we'll call this rectangle IJ. We'll just treat it as a general subrectangle of our rectangular region. So there is our subrectangle. As far as the dimensions of that subrectangle, we would have delta x and delta y, which is essentially the length of each subinterval along the x and along the y. Computationally, we would compute this, so delta x would really be b minus a over m. Right? How long is the interval divided by how many subintervals we broke it into, and then delta y would be d minus c over n. So that would get us the area of the base, and if we're talking about a rectangular prism, we're looking volume, which is area of the base times the height. So now we need to define the height of the rectangular prism on this subrectangle, which means we need to pick a point. I'm going to pick a random point, and we're going to call that point x sub ij, y sub ij. And if we evaluate the function at that point that we selected in the subrectangle, that is going to define the height of the rectangular prism. So we can start to build a little bit more. So we can say that the volume of the rectangular prism would be the area of, well, let's go height first because it's going to look nicer. So evaluate the function at the point x sub ij, y sub ij, times the area of the base, which is delta x times delta y. Delta x, delta y here, we're going to most often group this together and call this delta A, which is the area of the sub-rectangle that we broke down our region into. Now, as far as this random point that we chose to define the height of the rectangular prism, there's going to be some consistency in Riemann sum problems. Often we're going to choose it to be the lower left-hand corner, the upper left-hand corner, upper right-hand corner, or the midpoint, or the lower right-hand corner. Those are the 5 that we typically use as what we call sample points, the points that define the height of the rectangular prism we're using to approximate the volume. So now, if we're doing a Riemann sum, we're taking that volume of one singular rectangular prism and we're summing up the volume of all of the rectangular prisms we would get over all of the sub-rectangular regions. Which leads us to this, which is a double sum. So we have the sum from 1 to m for I and 1 to n for j, function evaluated at x sub ij, y sub ij, times delta A, which is the area of the base. First sum is our x's, our second sum is our y's, so moving along the x interval and then the y interval, and then in doing that, computing this value for each subrectangle gives us an approximation for the volume. This sum is known as a double Riemann sum, which approximates the volume of the solid bounded by a surface and the xy plane. And just repeating and formally defining, to compute this sum, we evaluate the function at the chosen point. Again, there's typically 5 points that we're going to be asked, as I went through on the last slide. Multiply by the area of the rectangular base, and then sum up the results. So just visually to get a sense of what a Riemann sum looks like in 3-space, so we have our first example where there are 16 rectangular prisms. M and n both happen to be 4 here. M equals 4, n equals 4. 4 subintervals along the x, 4 subintervals along the y. And then we broke it into even more rectangular prisms to get a more accurate approximation. And in this case, m is 14, n is 14. I counted that ahead of time, but you can count and double check them both to be 14. The approximation gets more accurate the larger m and n become. And this should be familiar to us. We are going to wind up taking a limit of that double sum. So the limit as m and n approach infinity of the double sum of f of x sub ij, y sub ij, delta A gives us the volume exactly. It no longer becomes an approximation, which then leads us ultimately where we want to go, which is a double integral. The double integral of the function f of xy over the rectangular region R in the xy plane is defined as that limit we defined on the previous slide. So we have double integral over the region R of the function f of xy dA equaling the limit as m and n approach infinity of that double Riemann sum. Just pointing out some notation here, we can see that there are now 2 integral signs to indicate we have a double integral. dA, we're integrating over an area when we're talking about a double integral, compared to dx or dy, where we were moving along an axis or an interval in single variable calculus, and we have a function of 2 variables. If the function, so if f of xy is greater than or equal to 0 over the region R, then the double integral is equivalent to the volume bounded by the surface and the xy plane. Essentially what this is saying is the function needs to be either 0 or above the xy plane, and then we have a defined volume. If the function's not always non-negative, then the double integral can be considered net or signed volume, which really just tells us any part of the function that goes below the xy plane is going to have a negative volume, or we're going to attach a negative sign to that volume, and then we compute the sum that way. So our first Riemann sum example estimate the volume bounded between the graph of the function 2x plus y squared and the xy plane over the region R, defined from 0 to 3 on the x and 0 to 2 on the y. So we have a rectangular region using 6 subrectangles with m equal 3 and n equal 2, and choosing the sample points at the. And then we're going to have two options here. Just breaking this down, highlighting again, m is telling us how many subintervals along the x and how many subintervals along the y. 0, 3 is our x interval, 0, 2 is our y interval. Just really highlighting some of the new notation and definitions here. So I've already generated the the rectangle, not the subrectangles yet. So here we have our rectangular region, 0 to 3 on the x, 0 to 2 on the y. If we're breaking to 3 subintervals, then it's just going to happen at 1 and 2. Then we have 3, and then 1 for y, and now we have our 6 subrectangles. Right, so we have 0, 1, 2, 3, 1, 2. Now the sample point for part A is at the lower left-hand corner of each subrectangle, which means here, 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 and here. So those are the 6 points that we need to evaluate the function at to define the height of each of the 6 rectangular prisms that we're finding the volume of. And then we're going to sum all of them up. So remember, volume of a rectangular prism, area of the base times the height. The nice part here is each base has the same area. Each rectangle, in this case it's a square, has the same area, so we can just factor it out and say 1 as the area of the base, and now just sum up the function values at each of our sample points. So at 0, 0, 2x plus y squared is 0, and then at 0, 1 we have 1. At 1 we'd have 2, and then y is 0, so 2 plus 0 is 2. At 1, 1, we'd have 3. At 2, 0, we'd have 4. And at 2, 1, we'd have 5. So using the lower left-hand corner as our approximation point, our sample point, the volume is approximately 15 cubic units, whatever that unit is going to be. Now for part B, we're going to change and now use the midpoints. So again, break down. Let's stick with black as far as drawing our subrectangles. Okay, so still 0 to 3 and 2, but our sample points are going to be the midpoint, so that's going to be 1 half, 3 halves, 5 halves, 1 half, 3 halves. So definitely going to be working with some fractions here. Sample points right in the middle of each square. So volume, again, base times height. Area of the base doesn't change, so 1. And now we have to evaluate the function at each of the new sample points. So at 1 half, we have 1 plus 1 half squared is 1/4. And I'll worry about simplifying everything later. Let's just evaluate. So at 1 half, 3 halves, we'd have 1 plus 9/4. And then at 3 halves, we're going to have 3. Y is 1 half, so plus 1/4. And then plus 3 plus 9/4. And then at 5 halves, 1 half, we'll have 5 plus 1/4 plus 5 plus 9/4. So we can simplify. Let's go and add the integers first. So 2, 5, 8 plus 10, so 18. And then 10/4, 10/4, 10/4 will be 30/4. We can reduce that to 15/2 while writing this as 36/2. 15/2. So that is 51/2. So our volume, using the midpoints as the sample points, is approximately 51/2 cubic units. So you can see they're close, but not that close, and that's going to be a byproduct of these approximations. There are so many sample points, the surface can really change quite quickly over a subrectangle. So these are just approximations getting us thinking in the correct way about volume, right? And that our double integrals are going to define volume once we get to actually evaluating them. Sticking with the theme of volume, the following iterated integral represents the volume of a solid. Make a sketch of a solid whose volume is represented by the integral and find the volume. So just as far as vocabulary goes, it's changed from double to iterated integral here because now the bounds of integration are put on each integral. Okay, they don't tell us which one dx and dy is, and that's something that we're going to explore more in the next video. But once the bounds are in, we call it an iterated integral based on the process we're going to use to evaluate them. Not relevant yet, but just wanted to point this out. If you notice the change in language, that's why we refer to some things as double integrals, if it's just double integral over r, as opposed to others as iterated integrals. And we'll review that again in the next video. So here we have 0 to 2, 0 to 2. So that's rectangular region, 0 to 2, 0 to 2. It doesn't really matter which one of those integrals was x or y since they're the same. And that defines the area we're integrating over. The function that we are integrating, f of x, y, is equal to 4 minus x. Or we can think about that as z equals 4 minus x. So they want us to sketch this first. So hopefully the region's not too difficult to draw because we also want to find the volume of the region. So x, y, z. So we can start by putting that rectangular base in. So 1, 2, 1, 2. Right, so there's the rectangular base that the volume is going to be defined over. And then we need to graph z equals 4 minus x. So 1, 2, 3, 4 on the z-axis. When x is 0, z is 4. When x is 2, z is 2. And that's going to connect as a line. And y doesn't change anything, so we can extend that out. That'll stay at 4. We can extend this out. That'll stay at 2. Connect it there. And then drop each corner down. So there we have our solid. And it is a trapezoidal prism. Two ways to find this volume. We can either treat it as a trapezoidal prism and find the volume that way, or you can split it up into two different solids and find their volumes. So we can split it into a cube and a triangular prism, or a wedge. Let's go trapezoidal prism just to review how to find the area of a trapezoid anyway. So we're going to treat this as a trapezoidal prism, which volume then is equal to 1/2 base 1 plus base 2 times the height of the prism, of the trapezoid rather, so I'll say height of the trapezoid, and then times the height of the prism. Okay, so let's start with the trapezoid. So this is our trapezoid face. So we have 1/2. The bases are going to be the vertical side, so this we'll treat as base 1, and this we'll treat as base 2. So 2 plus 4. Height of the trapezoid then is the height in between those bases, which is 2. And then the height of the prism is the side parallel to the y-axis, which is also 2. So 1/2 times 2, that's 1. 2 plus 4 is 6, times 2, so 12. So the volume of this solid is 12. Means if we were to do the integration out, we should get 12. We don't know how to integrate it yet. I'm sure you can speculate what that would look like, but if we were to actually go through the process of integration, we would get 12 as the answer to this double integral. Last question, use symmetry to justify that the following double integral equals 0 over the given region. So double integral of y dA over the region R which is the rectangle defined from 0 to 4 on the x and negative 3 to 3 on the y. So x, y. So the fact that we're trying to show that this double integral equals 0 indicates to me that we're talking about net volume, because y is definitely going to have some volume bound between it and the xy plane, and if this double integral equals 0, that means the net volume bound by this surface and the xy plane is going to be 0. So let's try to create a justification for that to be the case. So just so we can get a visual of the region, so we have x, y, 4, 3, negative 3. So our region, rectangular region there, that's R. So we can see that R is symmetric over the x-axis. Right? There's an equal number of points above and below. And that's going to be helpful for us. The actual function, f of x, y equals y, or you could think of this as z equals y. So we can try to sketch this in 3-space and come up with an argument in 3-space. That definitely works. But since this is only in terms of z and y, x doesn't affect the surface, let's just look at what it would look like in the yz plane. So in the yz plane, z equals y looks like that. And remember, the y interval we're on is from negative 3 to 3. So right now we're looking at more of an area argument, and if we can make an area argument, then hopefully we can extend it to volume. So here, in 2 dimensions, an integral represents the area bound by the curve in the x-axis. But in this case, it's the y-axis. So there's a positive area up here, an area that we would negate because it's below over here. And both of them happen to have the same area. Right? This would be 3 times 3, 9 over 2. Right? So this would be 9 over 2. And then this would be negative 9 over 2. So those areas would negate each other and wind up summing to 0. And because this surface isn't affected by the x, if we wanted to, if I put a dot right there and said we were looking down the x-axis, right, then this is what we would see for the surface as well. Right? It would be this surface extending out at us. This would be the volume underneath, and then this would be the volume below the xy plane. This would be the volume above the xy plane. I know I said underneath. Underneath the surface above the xy plane is what I meant. And those two volumes would negate each other. There would be an equal amount of volume above the xy plane as there would be below. So we could say that the net volume bounded by z equals y and the xy plane is 0. So, double integral over the region R of y dA equals 0. Hey, it's not a perfect argument, right? There wasn't exact math done. It was more of a reasoning argument, but the reasoning really helps us understand, or hopefully helps us understand, net volume. The fact that this surface is going to be above the xy plane for part of the region, below the xy plane for the other part of the region, and they're going to be equal amounts above and below, giving us a net volume of 0. So even though we would visualize it and we would see volume, the net volume bounded by this surface and the xy plane is 0. So each example highlights one of the important pieces. So we started with the Riemann sum, then we talked about volume, really connecting that idea of volume to double integrals, and then the last example we have here, talking about net volume or signed volume. Now that we established these concepts to build upon, our next task is going to be actually evaluating our double integration, and that will be our next video.